right, well, I think we should just get started, and if we have a couple stragglers, we have a couple stragglers. So this week we are excited to have Christine Task, who is the Director of Privacy Solutions at Nexus Research. She's been working with synthetic data since 2018 and has led 2 national challenges in differentially private synthetic data for NIST, served as the tech lead for the SenSyn synthesizer for the American Community Survey, lots of other things, and has also been leading NIST's Collaborative Research Cycle project. And I hope we get to hear about at least like half of those things today. So take it away.
You can even participate in that. All right, so first of all, check out NIST CRC on your various devices. If you Google it, what you will find is this website right here. And we'll explain more about that. But if you've got devices out and you want to find this website right here, you can do it now. And there's plenty of things to look around, and you'll be well prepared to ask questions. So how many folks here are like on the privacy engineering tech side? Show of hands. Cool. And how many folks are on like social or policy side? Privacy society. How about private good? How about privacy usability? Actually deploying things and making sure that they get used correctly and well. Okay, we got some selection. How many people know what differential privacy is, or have like encountered it, even if you don't feel like you have a deep understanding of it? Cool. How many people think that epsilon controls how private an algorithm is? Good. Well done.
I would have raised my hand.
Okay, well, so not necessarily in practice. All right, so let's go ahead and get started with that overview. All right, we're going to be talking about tools that NIST has developed to make available for industry and government and academia who are working on the problem of de-identifying data. I don't actually work at NIST. Nexus Research, I'm a contractor, but I've led a batch of programs for them. How many people have heard of NIST? Okay, good. That's great. So, National Institute of Standards and Technology. They exist to support organizations and individuals working on measurements essential to commerce, trade, and innovation. The idea is when things are moving from research to deployment, which is something I know that matters a lot to you guys, there's a lot of questions that arise about what's working well, what's safe to use, what actually satisfies the purposes of the organizations. And to do that, answer those questions, you need to build kind of a consensus scheme of measurement. And whether that's, making sure that you can test nutrition in food, whether you can do genomic research and break down the genome in the same way, or in this case, whether or not you can do data privacy. You've got to be able to build these tools. There's a lot that NIST does with privacy. So we're going to talk about data de-identification, but if you're interested, there's other things in federated learning. There are things for privacy policy. Out of curiosity, for folks who have had to work, and I know a lot of you guys have looked at in your master's projects, usability and specifically like workflow for organizations for doing the privacy policy. How many of you have heard about the NIST, it's this one right here, the NIST privacy framework, the NIST privacy framework? Fantastic. Okay, so there's our neighbors. We are next door to them. We're the ones working on evaluating privacy tech. This is what we've been doing it. So in 2018, so synthetic data. How many of you guys have heard of synthetic data? All right, let's explain that one a little bit. So synthetic data is, we have some data sets. It's full of people. It's very privacy invasive. We are going to make a new data set with a similar distribution, but none of the same people. We're going to make it up out of new fake people. That is delightfully ambitious, and in 2018, nobody thought you could do it, at least not with differential privacy. So we held a challenge where most of the participants and the people running the challenge thought that what we were going to all discover together was that you could not do differentially private synthetic data. But again, you got to get these consensus built, right? If that's true, we need to know about it. And so what happened was it turned out you could do differentially private synthetic data, but the method that worked was not the method that anybody expected to work. So for those of you who've heard of differentially private synthetic data or synthetic data before, has anybody got in mind like a technique you might use to do it? Have you heard about techniques for doing it? Right? So AI, right? I might train a GAN, give it a data set, train a GAN to learn what the distribution of that data set is, and then have the GAN generate a new data set. It looks like the original data set. How many people think that works? Good, okay, I like how you're genre savvy. Okay, so we thought it worked. In 2018, that's what we thought would happen. And right now, if you Google synthetic data, the first thing you're going to come up with is the synthetic data vault, and that's the techniques they've got. It does not work. I have not seen anybody get it to work. There are better approaches now, very recently, based on autoencoders. But the first thing that came right through was probabilistic graphical models. Anybody know about those? Like Bayesian network, Markov, and so on. Okay, so they're cool. What they do is they save the co-occurrence frequency of pairs of variables. We'll get into that more. Okay, we did a challenge. 2020, 2021, we did another challenge, and this time we made it even harder. We had, tons and tons of records per individual. We had math data, we had time data. Again, turns out that these techniques could be expanded to work on that. In 2022, we did the usability study. We went out to the census-like organizations, US Census, but also all over the world. And we said, come and join us for a week-long hackathon. And we're going to have you, we're going to give you some starter points, and we want you to try as many different synthetic data techniques as you can. We're going to give you a point on a leaderboard for each one you try, and we want you to evaluate them according to like what you think makes good data, right? Because these are not privacy people; these are data people. They did, and we came out from looking at all their reports, pulling all their stuff together, with a suite of like 24 different metrics we could use to measure the quality of synthetic data. Because when I said GANs don't work, you don't yet know what I mean by that, how they don't work, right? They don't work in interesting ways. We then grew that into a giant program, again, the international, where we are collecting, and this, how many people actually went to the CRC website? Cool. Go to the tab that says techniques. These are all the techniques that we have benchmarked over the past year and a half or so. Submitted, the proprietary ones are submitted by the companies that they run on our benchmark data. They produce synthetic versions of it, and then they actually turn in those excerpts of synthetic data, which we make public for anybody to analyze. And we're going to get to look at some here in a bit. Those are statistical tools, open source libraries, all sorts of things. We produce real detailed evaluation reports. All of that is public. All of that can be used for research. These days, when I want to do a paper on this, it takes me about 2 weeks to turn it out, because this is for anybody, because all of these things are sort of already partly done for you, and we want you to look at them more. Okay, so that all continues. I'm going to step back a little bit and talk about what the nuts and bolts of a data de-identification problem are. And then I'm going to pull out the PCA tool, which if you want to look ahead, that's under the Data and Tools tab. There's a lot of good stuff there. You scroll down, you'll see the PCA tool. And that's a point-and-click GUI interface. Actually get to explore the distribution of the synthetic data that gets made and see what's happening to it. I will say right now, the goal of synthetic data is to make the same shapes as the original data with new people. If you make the same shapes with the same people, you have failed. We don't have privacy. And that happens for differentially private techniques in the wrong settings. Meanwhile, if you make completely different shapes, also we have a problem. You would think that those were two trade-offs. You got utility or privacy, but you can fail on both. We have them make different shapes with the same people sometimes, where they'll drop a portion of the population and they'll exactly reproduce another part. So one thing that's happening here sort of accidentally is we're ended up doing fairly robust evaluation of the AI techniques. And something that's fun is that, or terrifying, take your pick, is that when we see what they succeed or fail at in terms of retaining the distribution of the data, that is probably also bias and artifacts that are creeping in anytime you're using these techniques to make predictions or classifications on tabular data like this. All right, but we're going to start all of this, and we wander now from privacy to statistics. All of this starts with the idea of a data record. We got a record on a person. If we're doing different for privacy, that means plus or minus one of these records is what we're looking at. When we're thinking about privacy, a lot of times we're going to split that into two sets of features. So features are the variables like age, sex, race, income, et cetera, and so forth, disease status. So features A, kind of think about as those are the ones we know about you. Features B, like something an attacker might know about you would be in feature A. Feature B might be the things that we are trying to find out about you. Right? So we'll get into privacy definitions in a bit here, but that's where you can kind of think about, okay, the distribution of the input data, right? So there is the data we're trying to protect. We feed into our synthesizer. It's got different clumps of people in different areas of the data space, right? In this case, we've got lots of people have value A1 and B1. Nobody has A1 and B2. That means that if I know your value of A1, what do I know about your value? If I know your value of A is A1, what do I know about your value of B? If I'm looking at the target data. It's got to be P1, right? Nobody's down here. So if I know that your value of A is A1, I know that you're in this column. I know you're up here. Now I know your value of B1. One way in which, an input data set might be disclosive. And the idea with the de-identified data, for the most part, is we're trying to make a same sort of shapes of data. And we're going to get into this more, but for right now, assume there are more complicated features here. Assuming I'm not talking about just two features, but that A1 and B1 are both, 6 or 10 features, and that the points and the locations of these points in space is meaningful, right? So this guy here has a different record value than this guy right here. So if I make the same shapes with different records, like I've done here, that is what we were trying to do. But of course, you can still infer something over here. So I might look at, and this is one of the things that differential privacy cares about, because differential privacy protects not only the places that people occupy, it also protects sort of people who are not in the data set, right? So we'd see some, if there was no public reason why you can't have A1 and B2, we'd see differential privacy add some noise there. A different type of privacy, how many people have heard of cell suppression? Okay, so cell suppression is what they did before differential privacy. And the idea is just this. If there is a combination of features that is too rare, then we suppress that. We suppress that combination. Either you can suppress the whole record, or you can asterisk out just the feature, you can blend bins, whatever. The fun thing is, differential privacy adds noise. Self-suppression, sort of erases part of the data. Which one do you think has more impact on the data in terms of the data quality? I think differential privacy? Self-suppression? Okay, so again, good job, Wasabi sort of folks here. It varies depending on the algorithm, depending on the way you do it. But as we get more and more features, and especially looking at diverse subpopulations, a well-tuned, good performing differential privacy algorithm will do better than self-suppression because it's not trying to erase this much of the data. You can look at, the signal here that I'm able to keep for these smaller populations sticks around, whereas with cell suppression, especially as you get more and more features, will erase people. And this is, we are about to hit the things that get very important because 4 years ago, COVID is memorable, right? And there had to be an argument made, and it had to be clear and understandable to everybody in the country, people who run businesses, people with state and local, there had to be a clear argument about safety. And the way we were able to make that argument was with COVID dashboards. People remember looking at COVID dashboards that would say, how are folks doing in your area? Is it spiking in your area? So those dashboards, and the CDC released data to support them, but the first dashboards were started by folks like you, and they probably saved lives. The CDC data, when it did come out, and it was a fantastic data source, but it used cell suppression for privacy. And that meant that it systematically erased minority folks from rural areas where they were minorities. Like, to get down to that county level, that meant they were outliers, they were subject to erasure. So CDC has been looking at techniques like this for things going forwards. You guys can also look at techniques like this. Anyways, that becomes important. Of course, also important is don't use a technique like this. So again, if you just Google synthetic data and you take the first thing that comes out of the search results, you get the synthetic data vault. It uses, again, it just destroys the distribution of the data. And we'll look at that for real here in just a bit. This is what we're going for. Same shapes, different people. And in terms of measuring privacy, you guys probably run into lots of different definitions of privacy. There's differential privacy. You talk about membership inference attacks, attribute inference attacks, re-identification, singling out, maybe. If we get to them, I've got slides on those. But in the core thing, and again, this one is just as important, what we're trying to accomplish when we de-identify this data is, could anybody use the de-identified data to do something bad that would make us regret having released it? Right? So when we make this data public, and when we make it public, it's out there for you guys to use. We need to have good quality on the data. We also need to have good privacy on the data. And you can think about that as like, this is coming from, evidence-based policy community. And the evidence-based policy doesn't have to be only government policy, like federal, also state and local, but also organizational business policy, right? You think about all the people that make decisions based on the COVID dashboards. Getting data out there is really important. But if you make data available that makes it so that people can be re-identified, especially vulnerable people, then maybe we have a real significant problem. So that's what we're going for. We will save the world. It's very crucial. I have incidentally, before I got to the slide, explained all of this. This is our benchmark data. So before you do anything like what we've done here, I'll remind you, and we went in 6 years from everybody believing you couldn't do this to, the 2020 census used differential privacy. There's a large number of government products using differential privacy or synthetic data now, and deployment's increasing. In order to coach that progress along, the first thing and most important thing you need is actually the benchmark data. This is the common problem that everybody's going to try and solve that's going to help us see where they're succeeding or failing at solving it. So here are some features, right? You've got income, education, we have race and ethnicity, we have housing type, which includes, are you in the dorms or jails, or do you have a house, number of people in your family, number of children, Hispanic origin, physical disabilities. So lots of interesting analyses that can be done here on the economic impact, education, vulnerable populations, and so on. It has these traits that we look for. They're real data from real humans. If possible, okay, two big mistakes you can make when you're testing your algorithm. First of all, everybody in privacy technology should be testing their algorithm. Two big mistakes you can make. If you test it on a problem that is too big and too hard, you won't notice when it fails, right? So it is totally possible for my algorithm, and you'll see some of this, to completely fail on some small portion of the population. And if I've got a big complicated data, I'll never see that happened. And it won't come out in my aggregate statistics on how successful I was, because it's only 5% of the population. It's only 3%, right? I did so great. I was like in the 90s, in terms of accuracy. But, so you don't want to do too big of a problem, but also you want to do real data, right? So you can make toy-sized versions of real data. It's nice to go start with like some artificial toy data to start with, but really, and NIST is a great place to look, and data.gov is a great place to look, you really want to try on real data, because you can have toy-sized problems that are easy for analysis, but they got weird broken things inside them that you won't ever see on the artificial data. This is what the diverse communities excerpt data actually looks like. So I'll tell you how we did this. We took the best performing synthesizer of all the ones that we tried out, and we found the communities in the US that it performed the worst on. And those are the communities that we selected for the benchmarking. You want to find the weirdest nut of the problem, but that's a toy-sized, accessible thing to go work on. Well, it turns out, without trying, right? We just found populations that were hard to synthesize. they were the really interesting populations. So this is Chinatown in San Francisco. This is University of Chicago, Obama's neighborhood up in Chicago, Hyde Park. This is Bethesda in DC. This is Cherokee reservations in Oklahoma. This is fracking areas in North Dakota. They're all real interesting places important for doing this sort of analysis. And if you go to that participate page, you'll see it's got a link to do this data. You can use this data for whatever purpose you want to. Now's a good time. I'll show you. All right. If you go to participate, you can come down here and it talks to you about, how to find the data. Here's the benchmark data we'd like you to de-identify. I've grabbed this. I think we link to this data on every site, every tab of the thing, actually. But you can find the data right here. It comes with metadata, dictionaries, features, recommended feature subsets. If you use this data, so it talks about synthetic, but you don't have to use this for synthetic data. You can use this for testing anything, and you're still going to be testing on these real-world diverse populations. If you use it, I don't know if anybody has wandered over to the research tab yet, but we have a research directory, and if you write a paper using our resources, we'll put you, and you let us know, we will link you up here. And you can go find everybody else who has done a paper using our resources. Because you're using the same benchmark data, if you find something weird happening in Chinatown and San Francisco, you can see who else found it, right? So we can all sort of look at it together. Anyways, so there is that. Under participate, these are all the instructions for joining our listserv, emailing, and so on. Okay. You guys have seen this. Techniques directory, evaluation reports, archive of data samples, talked about all that. Now for the fun thing. Pairwise PCA. So how many folks are familiar with what PCA is, principal component analysis? Okay, so is a nice easy way to say this, if I've got data that lives in a lot of dimensions, say like 24, if I've got data that lives in one dimension, like I just have, everybody's test grade. It's real easy to draw a distribution with everybody's test grade. I get a little bell curve. That's nice. If I have data that lives in 2 dimensions, I can still do that as a scatter plot. 3 dimensions, it's getting a little bit eye-watering, but I can do a 3-dimensional scatter plot. By the time I've gotten to 24 dimensions, we're not in this reality plane anymore. So what PCA does is it draws axes through the data in ways that have high variance. And that lets us basically take the 20-dimensional data distribution and smash it down into 2-dimensional pictures. We get more than one 2-dimensional picture because there was 24 dimensions to begin with. So you can think of these as just different. We sent an explorer with a cool-eyed camera out into the 24-dimensional data space. They took aesthetically interesting pictures, and that's what we have here. And when we say exploration or inspection tool, well, we say that we've got something that runs my battery down, is what we say. So let me grab my charger real quick. But this is the tool. So we're going to be able to pick things, select them, look through them, and actually understand how the privacy and accuracy are working out. Just for a moment while I naively assume that there's a good place to plug in under the app. There it is. Okay, here we are. So I'm going to start and make good on, and this is a fancier version of this tool that my company makes, but you can find the general version, which is locked to the CRC data on the website. If you keep scrolling down that tools thing tab. Okay, so here is a differential private histogram. And I am going to make good on my promise that sometimes even differentially private algorithms can exactly reproduce their input data. All right, here's our PCA picture. If I want to know, so I said these are axes through the data, so these are sort of combinations of features. I can look at which features were important and which principal components. So this right here is PC0 and PC1. So PC0 is a lot of education, income deciles, got a big weight on race. PC1 has a big weight on housing type, a big weight on own rent. This is my data, and if I see who uniquely exactly matches between the ground truth data, this is the input data up here in blue, and the differentially private data down here in green, it turns out that basically everybody exactly matches. In fact, 100% of the people came through. So this is not general. This is not just because epsilon was too big, because I can get very nice performance with an epsilon 10 on a different data set. The problem is that when I'm doing, so how many people are familiar with differentially private histogram? It's probably the simplest thing we do. So what we're doing for this is we're just counting the number of each type of person. So you'll note the feature, this is not 24 features, right? We've down selected the features significantly. And we're saying, okay, you got your specific record value. This is your specific combination of marital status and veteran and so on. And I'm going to say how many people are exactly like you. And then I'm going to do a count of that. Maybe there's 3 people like you. Maybe there's 10 people like you. Maybe there's 100. And then I'm going to add noise to obscure that count. And if my epsilon is 10, I am adding noise. It's not a lot of noise, in fact. It has a real low chance of selecting something even greater than 1/2. So it actually has a real low chance of changing that count. And in order to erase me, I have to get even luckier. It's got to select a large value on top of me that's negative. And most of the data space here is empty, right? Most of the things it's going to select and change by a little bit, not enough to actually change the count, are going to be out here in empty space. So if I go for, I'll show you another one where you can see the noise sort of filling in. But basically, because I've got exactly your record, exactly you, and I have just changed the count by 0.1, I'm not going to change the number of dots there that are there for you. So we just all go straight through. There's not entropy enough in the algorithm.
Can I ask a clarifying question?
Please.
So you're talking about histograms and counts,
Yep.
but I guess I don't quite understand how the scatter plot we're looking at, because to me, like, I look at the scatter plot and it's like 1 dot is 1 person.
Yep.
But the histogram is like, I'm envisioning like, here's the categories of people where there were like 1,000 people like this and 500 people like this and whatever.
So it's because you're using all of the values in the record. Mm-hmm. So I'm counting the number of people who was exactly like this person up here. In fact, if I select them right here, we can see exactly who this person is.
Okay.
Right. So.
Okay, so the histogram part is actually like taking collections of the dots and.
Yeah.
Okay.
Possibly making more dots on the same spot.
Got it. Okay.
Got
it.
Yeah.
Got it. Okay.
I had a question regarding, so like at the top it says all pairs there are 27,253 data points, and then unique records would be 2,773 people.
Mm-hmm.
Or and if are these points repeating, which is why the all pair shape is different, or what's the reason that?
So unique is okay. This is a good question. Unique exact match is a. Am I allowed to cuss in a seminar? Like, it is a not great privacy metric. It's a very simple one, right? And it's important to have it as a baseline. In fact, the work we're doing this year is all about improving our privacy metrics. But what it's doing is it is a unambiguous re-identification metric. It's saying first, we're going to assume only the unique records, only the people where there's nobody else like you out there. So I know this is exactly Bob. And then in the synthetic data, is there also only exactly one person like you? So now I know you were Bob in the input data, no confusion, you were straight, you were Bob in the output data. That has unambiguously leaked through. There's all sorts of re-identification, active inference, and so on you can do that's much more powerful than this. But the count is smaller because it's only looking at the number of unique records. So if there's not as many unique records, it's a smaller number. Yeah, please.
Just a follow-up to that. So continuing, the de-identified data and the synthetic data, is generated to a similar size as the original, that is 27,000 individuals.
Correct.
So would those 10% be falling into the catastrophic, like the leakage area where just because of the sheer number of records being generated, like DP will automatically end up leaking that data either way. Like suppression would be one way to solving the unique records problem, but
You won't leak it. So let me show you for the same algorithm performing a little bit better.
right.
Because what happens is if we increase the data spaces. So I want to get back to that, but let's do this for reference. Okay, so looking at 9, cache model. Okay, the same sort of thing. This is the differentially private one down here. This is the target one down here. If I do exact matches, you'll see that essentially every unique record survives through. And in fact, actually, when we do the check more thoroughly, basically every record, right, the unique ones and not unique ones, they basically all make it down here. Because we've added a feature, it's actually half of the data that's unique now in the target. And very nearly all of them persist through to the de-identified data. So I haven't changed the epsilon. I haven't changed the algorithm. The only thing I've done here is I've added another feature, so the space is bigger. And because the space is bigger, I'm rolling that noise die more times. When I roll the noise die more times, I've got a greater chance of actually erasing somebody like I tried to. I certainly have a greater chance of filling in noise in the rest of the data space, which is what you're seeing here. Okay, please you follow up, but like this, cool. This is what this tool's for, though, right? So we can illustrate these things. You can explore them. All right, so we've looked at differential privacy. We've seen that not so great differentially private algorithms. So I feel like next thing I should show you is a better performing one. So let's look at the winner of that first challenge. This is the one that showed us we could do. So there's better things out there now, but this is the one that showed us we could do differentially private synthetic data successfully, reasonably successfully. Okay, much better. So in here, we are, maintaining the distribution, but you can see that we are doing it with different people. It's not exactly the same shape as it was. And if I look at unique exact match, I'm still getting some leakage, but rather than 100%, it's 13%. And also, as we continue to increase the feature set here, that gets better. If I decrease epsilon, which I can do, so go back and select file, grab the one with epsilon 1. In a new update of this, we will have it sort them alphabetically. And here we are with epsilon 1. Interesting thing about the PGM technique this is using, so this is grabbing those co-occurrence of feature pairs. It's basically drawing a tree to capture the distribution of the data. Is because it asks so far fewer queries of the data, the performance actually doesn't change that much with epsilon. Because we're not having to sample noise that many times. You're actually getting a lot of the privacy out of the way the algorithm processes the data. And in fact, we'll see things that are not differentially private that perform, very similar on privacy and accuracy. Okay, so now that we've done some orientation on that, I'm going to ask you guys what you want to look at. So first, I'm going to run you real quick through these techniques. This is a subsampling of the techniques that we've got in the archive. The full thing's up on the website. But this is a TVAE is autoencoder, so that's the same sort of widget that's underneath ChatGPT. That's the new AI. K-anonymity, that's cell suppression. This is a genetic algorithm. So if you do genetic algorithms, you breed better data sets. So histogram. This is the AIM is the best performing of the current differentially private solutions out there. So it's the one that was developed after MST. CART is the one that actually gets used for the American Community Survey right now. So it's the best performing algorithm. I personally think overall, but there's a whole threshold of things to go look at. But it's not differentially private. It gets you real good privacy and utility, but it's not differentially private. Mostly AI is proprietary AI. SMOTE is geometric. PrivBayes is a Bayesian network, which is like a PGM, but it performs very differently than MST does because it asks a lot of queries. And when you do that in differential privacy, weird things happen. PACE-CT GAN is the best performing of the differentially private GAN techniques. Should take a look at that. It does weird stuff. And then MST we've looked at. So who's interested in the autoencoder? I guess what is, somebody raise a hand and request a synthesizer. What do you want to see? Yeah.
I'd love to see the fairness mode.
Fairness mode, awesome. Do you know what SMOTE is?
Yeah.
Okay. How do you think it's going to do?
I mean, it's gonna be. I'm interested in the fairness aspect, but yeah, it's gonna have a lot less utility because if it's gonna bias the data set or debias it, it's gonna reduce utility. But I think there'll be a lot of leakage of unique values as well.
Interesting.
Because they'll be basing it on them. But yeah, I have no idea actually. That's why I want to see it.
No, but this is good, right? This is why we do these things so we can test them. So I'll give you a heads up that it's SMOTE, but it's not, although it's fairness SMOTE, this is not being used to change the distribution of the data. We're still trying to copy the original distribution of the data. They're doing it with attentiveness to various subgroups in the population, which turns out to be important. And just to make sure that we don't erase or stretch or change them. So we haven't gotten into the highlighting things here, but you can do that. What SMOTE is for everybody else, it's fun. So I talk about, this is a 24-dimensional data space. The data sort of lives out there in this weird, non-Euclidean, heterogeneous, like crazy space because of categorical features, right? But we can still draw lines between them. We can pretend it's Euclidean. We can pretend that there is an ordering on things. And when we do that, we can say, okay, there's a batch of data points over here. There's a batch of data points over here. I want to make the same shapes with new people. Let's just sample more points in the basic space where people are. In fact, actually, let's go and draw a batch of lines between people, and then so interpolate, and then pick points to the right where those lines all intersect, right? So I'm going to find people that kind of look like my clumps of people. Maybe I'm going to get the same shapes. But how is it going to do for privacy? There's no differential privacy, and it definitely is dependent on where those points are. So let's see. Choose this one, and it's not national. And here we are. And we'll show you some more tricks here. So these are looking at sort of different pictures in the data, and you can see it's actually doing reasonably well at maintaining the shapes. I can check that. If I go look at the density, this will tell me the density difference. So this is where the synthetic data is producing more or fewer people than the original data. You don't show much, it doesn't show much there because in fact it's matching pretty well. You can look at that, so let's get out of density. Let's check out the unique exact match. So because we're now looking at all the features, a whole ton of features over here, now basically everybody's unique. Everybody is their own snowflake because I have so much information on everyone. And even though everyone is unique, so we are leaking 17% of the data. So yeah, so we are going to leak some people. Okay, but we are leaking fewer than the differential private histogram on the. I will say you also get good performance in terms of privacy on the nicely performing differentially private ones on this feature set once we get up to this many features, because more features, more noise sampling, bigger entropy. Yes?
Yeah, like I guess I'm interested, like the 17% seems to me a lot more defensible than 100%, partly because it would be kind of weird if you didn't have like any exact overlaps.
Yeah. You do get some that don't have any exact. So the some of the proprietary techniques, I think, go through and it can filter them out because why not? You know.
There was like I think one of the speakers from the previous week had a great graphic on a slide that I like a lot. That was sort of a graph of location data and all these sampled points that were replacing one of the points that we did not want to have in the data, and so you could just see this ring around the center of Pittsburgh. So it's like, I wonder what the original data point was.
Yep. No, I mean, that's also a problem. Yeah, you can leak, privacy by being a little bit too weird about how you erase things. That's another one where a lot depends on the distribution of the data. So in that case, in geography, you actually are in Euclidean space very literally, right? So you can get those holes. Here, it's a little weird, but this is the last chunk of the talk, which I will make sure to leave time to get to. Let's go look in the component definitions real quick, because I would like to show you the highlighting on race, but you can see that the race axis is not very important for the component I'm looking at the moment. So what I can do here is look for one where race is important. Hit it yet? No, marital status is super important. Cool. All right, let's show marital status instead. That's MSP, PC2. So we'll go grab a PC2 picture. This one, select feature. Why am I selecting race again? There are a lot of industry categories. This one, by the way. Who's working in universities? Exact match. Oh, there's marital status. Scrolled right past it. Okay, there we go. So here's another, you can kind of see how PCA is working. It's taking these different subpopulations and mapping them into different parts of the space. And you can see here that the distributions pretty much match. All right, so we're able to inspect something here. If you look at the evaluation report that we've got these sorts of information, but we also have a ton of additional information on correlations, on feature importance, on propensity, which you don't need to know about, on univariates, on all sorts of things. Let's back up. I want to show you one more thing. I haven't shown you GANs yet. I said terrible things about GANs, so I should back those up. Do this one. Okay, GANs. And this is on a simpler feature set. This is just the 10 features, not the 24. And this is the best performing. And the fun thing is that if you do, what's the fun things? If you do the univariates, so that's just show me the distribution of ages, show me the distribution of marital status, just one feature at a time, it does pretty well. But as soon as we get into higher dimensions, you see it's just losing it. And there's some things out there that do better, but the proprietary AI approaches, I think, do not do just GANs, and they tend to do a little better. I think actually do much better, so I'll show mostly AI real quick here, just to not impugn the whole thing. Right. So here on the same data is a better AI technique. Let's see how they do on that UEM, 0.03%. So they didn't go through and take out those people. They didn't really take them out in ways that are going to leave like a hole necessarily. Okay, so that is an example of how we go about this work of benchmarking these tools, making sure that they're safe to deploy, figuring out which things are good to deploy. And I think some of you may already be thinking about this. Once we have this, we can do meta-analysis, right? We've got all these guys. So where are there spots in the data that they're all having problems with? What about data makes things hard for different algorithms, right? So these are the sort of, if I want to build a train that doesn't explode, if I want to build a car that runs safely on roads, if I want to build an algorithm that's safe to deploy on data, it's good to know how the algorithm behaves under different hard parts of the data. What is the equivalent of an icy road for an algorithm running on data? And what we found out is that, so you're looking at heat maps that show how well an algorithm maintained the pairwise feature correlation. So this is the income relationship between housing type. Are you in the dorms? Are you in a nursing home? Are you in jail? Do you have a house? and income. Of course, there's a correlation there, but a whole batch of different algorithms that otherwise have nothing in common with each other all had difficulty maintaining that correlation. I mean, this is a statistical model. There's nothing in common with each other. But this is a hard part. We looked a little bit more, and you can actually see what some of them are doing, right? So this is looking at the correlation where we've got one feature up here, the other feature down here, and there's a red line if a lot of people have that feature combination. So a lot of people in this feature have that feature combination, and it's yellow if there's fewer, right? So here I'm saying, like, I'm living in a house, and there's a strong correlation to I have high income or something, or moderate income, right? And you can see that when the target data had this sort of complex, combination like this, some of the algorithms were kind of erasing that, we're simplifying it, right? And this is where we start to do some of the, interesting research to sort that out. Okay, and I will just plug this real quick. If you guys have been following, if any of you look at that, you can meet us if you give us an email, a heads up that you want to come to our office hours. Come to our office hours and we'll talk about research with you. Sarah, I will talk about research with you. We mentor a variety of students. You do something with our data, you get up here. Those same sorts of weirdness in the data will cause problems not just for de-identified data, but for lots of other pets as well. Anything where the behavior depends on the data distribution. Okay, what about privacy? So we shadowed this some. Here's a batch of techniques that do not suck. They're not erasing anybody. They are doing sort of okay, except for the self-suppression stuff. But for the most part, they're not erasing people. They're doing, reasonable utility. They're doing reasonable privacy. And now I want to know, which one am I supposed to use? So we're back to that privacy definition. How do we define privacy? It turns out there are very many different privacy metrics out there. And one nice thing you can do once you've collected, there's an iterative process here, right? We start with one data set. We get a whole batch of synthesizers. So we don't start with one data set. We get a whole batch of utility metrics. We get a whole batch of synthesizers. And now, because I have a batch of synthetic data sets, I can start benchmarking metrics. I can use those data sets to figure out which of the privacy metrics make any sort of sense out there. Because there are a batch of privacy metrics. There are sort of automated ways to say, okay, is this data really private? There are things that are better than my unique exact match. So attribute privacy, can I learn something invasive about you? We talked about this before. Here are two different library implementations. They're supposed to be able to determine, privacy metric, supposed to be able to determine if my data is good against attribute inference, right? So this is, I know A, I know these things about you, I'm trying to infer B. Anonymeter, but they're different implementations, like different ways of doing things. Anonymeter compares against the withheld data. So it's, can I learn something invasive about you better than I could learn just by looking at the withheld data that was never fed into the de-identification, right? Let's get a differential privacy-like definition. SynthPop wants to know that we fixed this problem up here with the input data. So did I at least make it harder to learn something about you than it was for the input data? Both reasonable definitions of attribute privacy. Differential privacy would help with that, right? Here we're looking at, so these are all, these are all the different techniques. So all these synthetic data samples, and this is how bad they are doing on privacy according to attribute inference, according to the anonymeter. One's looking at whether I can infer your income, the other one's looking at whether I can infer your veteran status. It's going, so this is the ground truth data right here. It should do as bad as possible, and we're seeing up is bad here, down is good. So if we don't de-identify the data at all, if we literally just feed it the ground truth data, and that's a good idea for benchmarking these things, then did it recognize that, in fact, you can definitely infer that attribute if you just have the same data you were given? Interestingly enough, it got in on one of them, but not on the other. So it thinks you've got good privacy. It thinks getting the ground truth data is still giving you good privacy for veteran status. That's not what we expect. That's something worth looking into. There's also not a lot of agreement when we look at the other metric. So this is research that we've been working on. This is some of what we're doing this year. We've been doing it for like a few weeks now. We will work more on explaining these things, but hey, that's fun. No agreement. Okay. Membership inference. You guys are familiar with membership inference, right? This is, can I determine if you were in the data fed into the model versus were you in the withheld data for a specific record? So for Tumult, they have a empirical privacy leakage metric that's looking to see, if there is, if you are a vulnerable outlier record, if there's not a lot of people like you, it's not in the big clump, you're out here, are there in the de-identified data people that look a lot like you, right? That I might infer that you were there. Meanwhile, Domius, under Sense City, is actually looking for those holes. So it's looking for sort of overfitting that happens kind of specifically from GANs, like dense little clumps. This is what these guys look like out of the box. We're going to adjust them because for them, 50-50 is confusion. That means I can't tell if you're in the set or not. So we're recentering them down there so we can compare them. Technically, I got to go back and multiply all this by 2 because we just recentered them. We didn't scale it up. So imagine this is, twice as tall as it is. Again, we're not seeing a lot of agreement. This is cell suppression right here. So they definitely think that cell suppression does not provide good privacy. It doesn't. But otherwise, they're pretty satisfied with privacy on a lot of the others. All the differential privacy ones, it thinks it's doing well on, although not perfect. I want to say, by the way, I don't know if you guys have run into this, but I love this about my community. We are actually seeing, so because this is a community that we have, we've pulled synthetic data, solutions from a variety of companies, that contribute to participate. They also often have privacy metrics because they have to evaluate their own tools. Would you expect that the privacy metrics would be harsher or less harsh on the data produced by the same company? Because it's actually harsher. In this community, what we've seen so far in this is that the people who are doing the privacy metrics, if we've also got a sample from them, they chose a privacy metric to hunt for the weaknesses of their tool. So one of the harsher scores that we see on the differentially private techniques comes from Tumult that works on differentially private stuff. That's a good, they're well prepared to tell you what epsilon you should use. Okay, can I find you? So those two definitions kind of make sense from a computer science perspective. We also have definitions that kind of come from a legal perspective, and they're coming kind of still from the anonymity work that pre-existed all this. So re-identification is this idea of, did I anonymize the data or can I actually still find you in there? And so, unique exact match is a identification, re-identification metric. This one's fun, linkability. So if I had data set B, and this is a good commercial marketing application, right? I've got data set B that has some information about you, and I've got data set A that has some different information about you. Can I link up A and B using the released data? Talk about real privacy threats, being able to use data that's out there to, re-identify vulnerable people with protected statuses. This is the sort of thing you're worried about. And just like, this little gap in the data creates a problem here. Yeah, we could use this de-identified data to link up Bob. Okay, so there's two metrics looking at this. And there they are. Linkability turns out to be hard to do in practice. It gives a perfect score a privacy score to basically everything on this data set. Meanwhile, unique exact match actually has this curve that, although it's a terrible privacy metric, I'm kind of thrilled, looks like the Tumult metric in terms of where it votes on things. Okay, last one, singling out. So this is more the European definition. This is looking at the de-identified data. Do I feel like I found you? Is there somebody weird in the data set, in the de-identified data set, sort of an outlier? And for some reason, I feel that there's real substance to that outlier. That might be you. The fun thing is, this goes in, there's two ways you could do this, right? So the legal definition is kind of vague. And so we've got two metrics that look at two different directions. One metric, identifiability, says Bob's a weirdo in the input data, and there's de-identified people who are too close to Bob. The other one goes the other direction. Jan is a weirdo in the de-identified data, and there's too many weird people who look like, yeah. They don't agree either. They sort of agree, but they sort of don't. And if I want to choose which of these products I'm going to use, and I make my choice based on one but not all of these metrics, that's great. In fact, nothing agrees with anything. So if we scale them all to be on the same range, it looks like this. But is there consensus? What if we only look at author-tuned metrics? So for some of these, and this is a real great community, we've actually had the makers of the libraries configure them for our approaches. You'll notice like a lot of these metrics, we're talking about similarity. Who's too close? And this comes back to this problem that if, this is close to this, I can say that unambiguously because this is three-dimensional Euclidean space, I can measure it. When I'm talking about features like age is easy, it's also got numbers. If I'm talking about things like race and industry and all these sort of complicated things that are not ordered, what is the distance between a race of 6 and a race code A and a industry code Q, right? Versus a industry code B and a race code W or something, right? Like I don't have an easy distance thing. So hidden in all of these metrics and not necessarily brought out in research papers, not necessarily something we hit until we get here, is the definition of a similarity metric. We kind of suspect that's probably producing some of the differences in behavior. If they tune the metrics themselves, then we get better stuff. We want to learn how to auto-tune them. You can help. So what we are launching, and you'll probably hear this again this spring, is there is going to be a red teaming exercise where we're going to ask you guys to try to do membership attacks, inference attacks, attribute, et cetera, on our data, on this data, because we suspect as you do it, we're going to learn a lot about how you configure these things to be successful, where that differs from how the metrics are being, configured by default. Maybe lots of other stuff. We are looking for, and we'll be recruiting from you guys, also from social science and statisticians, who may have real good ideas of what it means for one person to be like another person. We do this, again, all up in the open. You get to learn from everybody. There's leaderboards, there's office hours. And we're real good about getting names up on the website, so it's not bad CV credit. Okay, so it's not up on the website yet because we're not launching until 2025. It's going to be launching in April, but there will be updates. And if you sign up for our listserv, everybody who's been hanging out on the website, all the way up to the top here, participate. I'm off the internet. If you go to the participate tab, which you've all found before, it gives you the email to contact us if you have questions. It also has the listserv. We don't spam you. You sign up for the listserv. We'll tell you when interesting things are going on. Okay. Thank you very much. Surgically tailored this so we have 2 minutes left. Does anybody have a 2-minute question? All right, well, if you do, sign up for our listserv, come to our office hours, ask me questions.